There are several steps to follow for graphing a rational function. First, factor the function and simplify. Any factors canceled out of the numerator and denominator are going to be wholes of the function. Then evaluate the function at 0 to find the y-intercept. Step 3. Find the x-intercepts by setting the numerator equal to 0. Determine the behavior of each graph at each x-intercept based on its multiplicity. Step 4. Determine the vertical asymptotes based on the factors of the denominator in lowest terms. Determine the behavior of the graph on either side of the vertical asymptote based on the following. If the multiplicity of a factor is odd, the graph will approach opposite infinities. So what we mean by that is if you have a vertical asymptote, on one side the function will be approaching positive infinity, and on the other side of that vertical asymptote the function will be approaching negative infinity. So this is an example, or we could have had it this way where on the left I was approaching negative infinity and on the right I was approaching positive infinity. So opposite infinity, so if it's an odd factor, so for example if you had something like x plus 1 cubed in the denominator, this would have a vertical asymptote of x equals negative 1 with an odd multiplicity, so I'd be going towards opposite infinities there. If the multiplicity of a factor is even, the graph will approach same infinities at the vertical asymptote. So either the graph will be going towards negative infinity on both sides, or it'll be going towards positive infinity on both sides. So that's what we mean by same and opposite infinities, and this really helps us with graphing. Step 5. Determine the horizontal asymptote of the function if one exists. Determine points, if any, at which the graph of R intersects this asymptote. So remember that we can never intersect a vertical asymptote, but we can, in the short term, intersect a horizontal asymptote. So to figure out if we ever do intersect it, you set the rational function equal to the horizontal asymptote and solve for x. You graph the asymptote using a dashed line and then plot any points at which the graph of R intersects the asymptote. And then use the results of steps 1 through 5 to graph the rational function. Let's put these steps to work. Graph the rational function R of x equals x minus 1 all over the quantity x squared minus 4. So step 1 said to factor the function and simplify. Any factors canceled out of the numerator and denominator are wholes of the function. It looks like the numerator does not factor at all, but the denominator does, into x minus 2 times x plus 2. Looking at this rational function, I see that there's nothing that can cancel out. Step 2. Evaluate the function at 0 to find the y-intercept. So we'll substitute in 0 for x, and I get 0 minus 1 all over 0 minus 2 times 0 plus 2, which gives me negative 1 over negative 2 times 2, which is 1/4. So my y-intercept is at 1/4. Step 3. Find the x-intercepts by setting the numerator equal to 0. So that our numerator is x minus 1. That will equal 0 when x is 1. Determine the behavior of the graph at each x-intercept based on the multiplicity. So the multiplicity of this factor is 1, which is an odd number. So that means the graph will go through at that x-intercept. Step 4. Determine the vertical asymptotes based on the factors of the denominator in simplified form. If the multiplicity of a factor is odd, the graph will approach opposite infinities, and if it is even, it will approach same infinities. Looking at what we found in step 1 for the simplified version, our vertical asymptotes are going to be at x equals 2 and x equals negative 2. We can also see that this vertical asymptote, for both of these, the factors were to the first power, which means that they had odd multiplicities. So given that each of these have odd multiplicities, they're going to be going towards opposite infinities, both of them, on either side of the asymptotes. Step 5. Determine the horizontal asymptote of the function, and then determine the points, if any, at which the graph intersects this asymptote. So I'm going to go back actually and look at this function because it's in expanded form to figuring out the horizontal asymptote. So remember, we find that by looking at the degree on the numerator and the degree of the denominator. The degree of our numerator is 1. The degree of the denominator is 2. So the degree on top is smaller than the degree on bottom, which means that we have a horizontal asymptote at y equals 0. Now to determine if we intersect this asymptote, you set your function equal to that. So multiply both sides by x squared minus 4. And we're left with 0 equals x minus 1. So we get that x equals 1. So yes, we intersect the horizontal asymptote at x equals 1. And now we'll put all of these pieces together. So the first thing that I do is I draw in my asymptotes with dashed lines. So we have an asymptote at x equals negative 2 and an x equals 2. And again, notice that I wrote these as equations of lines. I didn't just write 2 and negative 2. I wrote x equals 2 and x equals negative 2. I also have a horizontal asymptote at y equals 0. And then I substitute in my points. I have a y-intercept at 1/4. And I have an x-intercept at 1. So now this is the part that you kind of have to use some, like all of these steps 1 through 5, are basically our puzzle pieces, and now we have to put all those pieces together to see how this graph is going to look. So this is the part that takes a little bit of practice to get there. I'm going to give you a bunch of examples, but I'm going to ask you as we're going through this video and you start to feel a little more comfortable to pause it before I finish up the graph to see if you can do it on your own first, and then watch me do it. But obviously for the first few examples, watch me do it first to kind of get the hang of it. So I have these 2 points, so I'm going to connect them. So now I'm going to see what happens here at this x equals 1. So either I'm going to go up or I'm going to go down towards that vertical asymptote. If I went up towards the vertical asymptote, that would mean that I only touched this, this x-intercept. We said here that at that x-intercept I have to go through, so this forces this graph to have to come down. I can't go back up again because if I did, I'd have to cross the x-axis, which I don't have any other x-intercepts. So by process of elimination, this forces this graph to have to go down. Now I have to look at what happens on this side. I'm either going to go up towards positive infinity or down towards negative. If I go down towards negative, I'm going to be crossing the x-axis again. I only have one x-intercept, so that means I can't cross it again. So this forces this to have to go up towards positive infinity on that side. Now when you do your vertical asymptotes, basically what you do is you're separating out your graph. So we're always going to have, basically however many asymptotes you have, you're going to have that many pieces plus 1. So I had 2 asymptotes, so this graph is going to have 1, 2, 3 pieces. So looking on the left-hand side for this piece, I'm either going to be above or I'm going to be below this horizontal asymptote because I only intersect it and cross it at x equals 1. So I know I don't cross it again. So this is where this opposite and same infinities comes in. So at this vertical asymptote, x equals -2, I have opposite infinities. So since I'm going up towards positive infinity on the right, this forces me to be going towards negative infinity on the left-hand side, which means that this piece has to be there. Looking over on the right-hand piece, again, I'm going to either be in that quadrant or down here. So this is where the opposite infinities comes into play again. At x equals 2, I was at opposite infinities. So since on the left-hand side I'm going down, this forces me to be going up on the right-hand side so that they're going in opposite directions. So there's your sketch of the graph. Graph the following rational function. R of x equals x squared minus 9 all over the quantity x squared plus 9x plus 18. Step 1 is to factor the function and simplify if possible. X squared minus 9 factors into x minus 3 times x plus 3 all over x plus 6 times x plus 3. This means I can cancel out an x plus 3 term, which means that I'll have a whole at x equals -3, because that whole occurs when that canceled out factor will equal 0. And this simplifies into x minus 3 over x plus 6. So the big thing as you are working through the rest of the steps here is that we use the simplified version from here on out. So I'm going to box that and put some stars near it so I remember that this is the version that I'll be using to answer the rest of the questions. For step 2 is to find the y-intercept. That's when you let x equal 0. So when I substitute in 0 for x, I'm left with 0 squared minus 9 all over 0 squared plus 9 times 0 plus 18. When I simplify this, I get -9 over 18, which is -1/2. So that means that the point 0, -1/2 is on this graph. That's our y-intercept. Step 3 is to find the x-intercepts, and those are found by setting the numerator equal to 0. Again, we're going to be using the simplified version. The numerator is x minus 3, and that will equal 0 when x is 3. So that means we have an x-intercept at the point 3, 0, and that has a multiplicity of 1 to the first power. So that means that it's an odd multiplicity, so we'll go through the function, or the graph will go through at that x-intercept. Step 4 is to find the vertical asymptotes. Vertical asymptote is found when the denominator of the simplified function equals 0. Denominator is x plus 6, so that will equal 0 when x is -6. So this means that our vertical asymptote is at x equals -6. Again, make sure that you're writing this as an equation of a line. Now, the other part of this step was to see if at that asymptote, the function went towards the same or opposite infinities. This factors to the first power, which is an odd multiplicity, so this means that these will go towards, the function will go towards opposite infinities at that asymptote. Step 5 is to find the horizontal asymptotes. So the leading term on the top is x, the leading term on the denominator is also x. Those are both to the first power or degree of 1. So since the degree on top is the same as the degree on bottom, the horizontal asymptote is going to be found by dividing those leading terms. So we get a horizontal asymptote of y equals 1. The other part of step 5 was finding if we at all ever cross the horizontal asymptote, and that's found by setting your function equal to that horizontal asymptote. And again, you're always using the simplified version. And we end up with x minus 3 equals x plus 6. Get all the x's on the same side, and you're left with -3 equals 6. -3 can never equal 6, so this means that I do not cross the horizontal asymptote. Now I can put this all together. So to do that, the first thing I do is I graph the horizontal and vertical asymptotes. So we have a vertical asymptote at x equals -6. And then one at y equals 1. Now I graph my points. So I have a y-intercept at -1/2 and an x-intercept at 3. Connecting those together, I know my graph is going to at least have that part, so now I need to figure out what the next part's going to be. I'm going to start at this 3. So at x equals 3, we found that the graph is going to go through there. So that forces this graph to have to go up. It can't go back down because that would mean that we were just touching at that x-intercept. And there are no other x-intercepts. So now I need to figure out this y-intercept. Am I going up towards positive infinity or down towards negative infinity? If I go up towards positive infinity, that means that I cross the x-axis again. And I also go intersect the horizontal asymptote. I found through my steps that I never cross the horizontal asymptote and I only have this one x-intercept. So that means that the function cannot go up towards negative infinity. It has to go down here towards, or up towards positive infinity. It has to go down towards negative infinity. The other piece we have to remember is to put our whole at -3. Now I need to figure out if I'm above or below here. I'm above the asymptote if I'm going towards positive infinity, and I'm going to be below the horizontal asymptote if it's going towards negative infinity. This is where step 4 comes into play. I found that these were going to have opposite infinities. So on the right-hand side, since this graph is going down towards negative infinity, on the left-hand side of the asymptote, I must be going towards positive infinity. Now again, I know I can't cross this horizontal asymptote because I found in step 5 that I never cross it. So that forces this graph to have to look like this. Now, if I wanted to be a little more exact, what I could do is I could have found exactly where this hole was going to occur. To do that, you plug that x value into your simplified function. So I get r of -3 equals -3 minus 3 over -3 plus 6, which gives me -6 over 3, which is -2. And that's basically where I put the point, which was good. So again, if you want to be a little more exact about where your hole is, just plug in that x value into your simplified function, and that'll tell you where that hole should go. Graph the following rational function. R of x equals the quantity x squared plus 3x minus 10 all over x squared plus 8x plus 15. My best advice at this point is to actually pause the video and try to work through at least the first 5 steps on your own, if not the 6th step. Afterwards, watch this video and watch me work through it to see if you made any mistakes or if you're getting this concept down. Okay, step 1 is to first simplify. When I factor this function, I get x plus 5 times x minus 2 in the numerator, and x plus 5 times x plus 3 in the denominator. This means that I can cancel out an x plus 5 term. So there will be a hole at x equals -5, because again, it's whenever that factor will equal 0. So this simplifies my function into x minus 2 over x plus 3. If I want to find that exact value of that hole, let's do that really fast. When I plug -5 into my simplified function, I get -5 minus 2 over -5 plus 3, which is -7 over -2, which is positive about 3.5, or exactly 3.5. So right now I'm actually going to graph that hole just so I don't forget it, because sometimes it's very easy to forget those holes at the end since that's the first step that we do. Step 2 is to find the y-intercept by substituting in 0 for x. Again, I'm going to use this simplified version. and that leaves me with negative 2/3. So that means we have a y-intercept at negative 2/3. Step 3 is to find the x-intercepts, and that's when that numerator equals 0. X minus 2 equals 0 when x is 2. That has a multiplicity of 1, so that means that the graph will go through at that x-intercept. Step 4 is to find the vertical asymptote, and that's when your denominator is going to be equal to 0 in the simplified function. X plus 3 equals 0 when x equals negative 3. So I have a vertical asymptote at x equals negative 3. This is to the first power, so that means that they'll be going towards opposite infinities there. Step 5 is to find the horizontal asymptote. Leading term in the numerator is x. Denominator is also x. Those are both to the first degree. So that horizontal asymptote is going to be found by dividing the leading terms. And I find that I have a horizontal asymptote at y equals 1. Next, I find when I'm going to cross the horizontal asymptote, if at all. So set that simplified function equal to that value. I'm going to multiply both sides by x plus 3. And I'm left with x minus 2 equals x plus 3. Get all of the x's onto the same side, and that leaves me with negative 2 equals 3. Negative 2 will never equal 3, so that means that I never cross the horizontal asymptote. All right, now that I have all of my steps, I can go through and start graphing. So vertical asymptote is at negative 3. Horizontal asymptote at y equals 1. I have an x-intercept at 2 and a y-intercept at negative 2/3. Forces this part to be graphed there. All right, so now at 2, does the graph go through, or does it just touch and go down? So it looks like at that x-intercept I said I go through, so that means that this graph has to go up in this direction. And again, it never goes back down because I'd have to have another x-intercept and I only have one. So we'll hug our horizontal asymptote there. Now I need to figure out, is the graph going to go up towards positive infinity or down towards negative infinity? If I go up, I'm going to cross the x-axis again and the horizontal asymptote. I don't cross the horizontal asymptote, and I only have this one x-intercept. So that forces this to have to go down here. Now I already have a point, so I can already tell I'm going to be above the horizontal asymptote on the left-hand side. But just to check, again, let's go through and make sure we've done our math right. So we found that we had opposite infinities at that vertical asymptote. So since I'm going down towards negative infinity on the right-hand side, that means this has to be going up towards positive infinity on the left. And there we go. Graph the following rational function. R of x equals x plus 2 all over the quantity 2x squared minus 2. Step 1 is to simplify. The numerator can't be factored anymore, so that stays as x plus 2. For the denominator, I can factor 2 out, and I'm left with x squared minus 1. I can actually factor that further because x squared minus 1 is the difference of perfect squares. So that leaves me with 2 times x plus 1 times x minus 1. And in this case now there's nothing that I can factor out. So I'm just going to leave it. Okay, step 2, find the y-intercept. Substitute in 0 for x. Get 0 plus 2. And I'm actually, since we didn't have any simplified version in step 1, this is the same thing, it's just factored of the original function. I'm actually going to use this original function for this problem, this part, just because I think it'll be a little bit easier. So this leaves me with positive 2 over negative 2, which is negative 1. So we have a y-intercept at 0, negative 1. Now, if you wanted to, you could have used this factored version of this function and you would get the exact same answer. Step 3 is to find the x-intercepts, and those occur when the numerator equals 0. So that means we have an x-intercept at -2, 0. This has a multiplicity of 1, so that means that the function will go through at that x-intercept. Step 4 is to find the vertical asymptotes. So the vertical asymptotes are when the denominator equals 0 of the simplified version. So this denominator is going to equal 0. 2 is never going to equal 0. X plus 1 equals 0 when x equals -1. And that's to the first power, so that means it has an odd multiplicity, so we'll be going towards opposite infinities. And then this factor, x minus 1, is going to equal 0 when x equals +1. Again, this is to the first power, so this is going to also have opposite infinities. Step 5 is to find the vertical asymptote, or the horizontal asymptote. I'm going to again use this version of it. So we can see that the leading term on top is x and the leading term on bottom is 2x squared. So the degree on top is 1 and the degree on bottom is 2. Since the degree on top is less than the degree on bottom, this means we have a horizontal asymptote at y equals 0. To find out if I'm ever going to intersect this horizontal asymptote, we'll set our equation equal to this. X plus 2 all over 2x squared minus 2. Multiply both sides by 2x squared minus 2. And we're left with 0 equals x plus 2. When I subtract 2 from both sides, I get x equals -2. So I will cross that horizontal asymptote at x equals -2. Which makes sense because, again, this was the horizontal asymptote had a y value of 0, and I already found that point. When y is 0, x is -2. Okay, now we have all of our pieces, and we can graph this. Horizontal asymptote at 0, vertical asymptote at -1, and then again at 1. So this means that this graph is going to have 3 pieces, one here, and one here. Let's start with the points that we have. So I know that the points are going to be at -2, 0. And then I have another point at the y-intercept, which is -1. Whenever I have things split up into 3 parts, I usually always start with the middle part, because if I can do that part, then using these opposite infinities will really help me with knowing where the other pieces go. So the first one in the middle, if I go up towards positive infinity, I'm going to be crossing the x-axis, so I'd have another x-intercept, and I'd also be crossing the horizontal asymptote at a value other than just x equals -2. So that can't happen. Same thing on the left-hand side of that point. If I went up towards positive infinity on the left, same issue. I'd be crossing the x-axis again, which would mean I'd have another x-intercept, which I don't. So this forces these, by process of elimination, that we know that this has to go down towards -infinity on both sides of that point, that y-intercept. All right, so now let's start with this part of the graph. So here I'm either going to be going towards positive infinity or towards -infinity. So I'm either going to be here or here. I found that at x equals 1, which is what that vertical asymptote is that created that region, that I go towards opposite infinities. So since on the right-hand or the left-hand side of that vertical asymptote I'm going towards -infinity, that means on the right-hand side of that vertical asymptote I must be going towards positive infinity, which means that the function is going to be up in that quadrant. Now looking over here, again, I'm going to be either above or below that horizontal asymptote, or even both, because I actually cross it, we found at -2. So let's see where I'm going to start. So I'm either going to be going towards positive or towards -infinity. So again, for this one, I found at x equals -1, we are going towards opposite infinities. So since on the right side I'm going towards negative, that means on the left I have to be going towards positive. Now, this is where it gets a little weird. So I cross this horizontal asymptote. Now, at -2, I go through. So that means I have to go down into this part. But then I always have to go back up and hug that horizontal asymptote at the end. I don't go above the horizontal asymptote because I only cross it at x equals -2, so I can't cross it again. But you always have to hug that horizontal asymptote on either ends.